Hi, my name is John Bayley. I, along with Tim Kosterzitz, under the supervision of Drs. Joey Key and Matthew DePease, conducted research into the gravitational wave signature of cosmic string loops. In this presentation, I will talk to you about cosmic strings, cosmic string loops, provide a general overview of gravitational wave detectors, and then present the methodology of our research. What are cosmic strings? Cosmic strings are one-dimensional topological defects that would have formed during phase transitions in the early universe. Similar to how steam is more symmetric than liquid water, which is in turn more symmetric than ice, the universe began to cool after the Big Bang, and this caused breaks in field symmetry. As these fields took on different vacuum states, or in other words, different ground state energy levels, the difference in energy between the states took the form of cosmic strings. An example of this is shown in Figure 1. While other topological defects, such as domain walls and monopoles, are possible, my research focused on cosmic strings and creating a template by which to detect the loops produced by them. The motivation for the research into these strings and loops is the role that they could have played in galactic formation. Cosmic strings are predicted by most every grand unified theory and could have played an important role in forming the large-scale structures we now observe in the universe. In addition, they could provide an explanation to the anisotropies observed in the oldest light of the universe, the cosmic microwave background. There are two ways to detect cosmic strings: via gravitational lensing and the gravitational waves emitted from cosmic string loops, cuffs, and kinks. This is what I focused on. But how are cosmic string loops formed? Cosmic string loops are formed one of two ways. Either a string intersects with another string, as shown in illustration A of Figure 1, or a string doubles back on itself and breaks off a loop, as shown in illustration B. My research focuses on these loops and the gravitational waves that they emit. By creating the template of the gravitational wave signal, the gravitational wave observatories can use the template for comparison with data gathered at their detectors. The goal is to create a template these detectors can use to make a successful observation of a cosmic string loop. The three gravitational wave detectors I want to discuss are LIGO, the Laser Interferometer Gravitational Wave Observatory, NanoGrav, the North American Nanohertz Observatory for Gravitational Waves, and LISA, the Laser Interferometer Space Antenna. Now, LIGO is a modified Michelson interferometer. In principle, it shines a laser down to a beam splitter, where that beam of light is split in two with 90 degrees offset between them. The beams then travel down 4-kilometer arms, where they are reflected and recombined at the photodetector. Normally, the 90-degree offset would provide total destructive interference, and no pattern would be observed at the photodetector. But if a gravitational wave travels by, stretching and squeezing spacetime, it will change the path of travel for the beams. When collected at the photodetector, there will then be an interference pattern generated by the passage of these gravitational waves. LISA will operate with a similar concept, but a major difference between LIGO and LISA is that LISA will be a space-based observatory launching in the 2030s. It will not have to deal with the terrestrial noise that currently affects LIGO. It will also be able to detect lower frequency gravitational wave emissions by virtue of its longer arm lengths, which are approximately millions of kilometers each. NanoGrav is a galactic scale gravitational wave observatory. It uses radio waves generated by fast-spinning neutron stars to monitor the pulsar timing. By creating an accurate map of these pulsars in the sky, NanoGrav can use this data to detect shifts in the signal's time of arrival and make observations of high-mass objects emitting gravitational waves. With arm lengths of galactic scale, NanoGrav has the lowest frequency sensitivity of the three observatories. These detectors are all sensitive in different frequency bands and will detect different types of gravitational wave sources. In addition, the gravitational wave signal from cosmic string loops is a broadband signal. Because of this, the signal from a cosmic string loop is potentially detectable by all of these observatories. The signal generated by cosmic string loops is harmonic in nature. When modeling the signal, the harmonic nature of the signal is apparent in the frequency domain. We expect to see a power amplitude drop-off proportional to 1 over n to the 4/3. The equation h of t models the continuous time domain signal from the cosmic string loop. Since we cannot observe for an infinite time, we need a discrete time series as shown in equation 2. Equation 2 is essentially the continuous time domain signal multiplied by an integration time or period of observation t. For example, Lisa would have an approximate sampling rate of 10 Hertz and an integration time of 1 to 3 years. Using h of j, we generate data points in the time domain that can be input into the discrete time Fourier transform. The discrete Fourier transform, equation 3, then uses the time domain signal data points and breaks the signal down into its constituent frequencies and associated power amplitudes. Some variables of note in equation 2 are h of j, the dimensionless strain, p sub n, the power amplitude per mode, and g mu, the string tension. To date, I have been able to write the code necessary for generating the gravitational wave signal template. While still in need of refinement, the code provides a good foundation for moving forward. The amplitude depends on n, an integer representing the mode number, and should scale proportional to 1 over n to the 4/3. The next step is to include this dependence so the frequency domain template reflects this proportionality. The Gravitational Wave Observatory search for these signals from cosmic strings. Currently, non-detections put limits on the physical parameters of the cosmic strings. In other words, the strength of the signal emitted by cosmic strings is less than the sensitivity of the current observatories. So, detector sensitivity, or our methods of data analysis, must be improved to continue our search for cosmic strings. Here is a list of my sources, and thank you for listening to my presentation.